Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last lecture, we were looking at the first order conditions for constraint optimization when there is single variable. So, we will be continuing in that. So, we can now write down the conditions for first order case when we have constraint optimization but single variable as follows, that dz by dx is equal to uj times dgj by dx. Okay. So, this was the case that we had seen before. So, in this case either j was equal to 1 or j was equal to 2, but now we are replacing it with this condition here. Okay. That is dz by dx is equal to summation of uj dj by dx. So, now this OR condition is not required. So, regardless of which of these two constraints G1 or G2 is the binding one, we will have U1 and U2 defined. Okay. Now, the unconstrained minimization case can be considered as a constrained minimization case with an internal minimum point. Why is that the case? Because in this case, when the optimum point is lying in the interior of the two boundary points, then neither of the two binding constraints is actually binding. Okay. So, in that case u1 will also be equal to 0 and u2 will also be equal to 0. Why? Because we had looked at this condition beforehand, that in the last lecture, that if a constraint is not binding, then for that constraint the corresponding uj will be equal to 0. So, if we have this kind of condition that we are minimizing a function zx, okay, and this is a dash and this is a double dash. So, the minimum occurs here. So, at this point the slope is equal to 0. Okay. So, this is the first case that we had seen. Okay. So, in this case both of the two constraints G1 and G2 are non-binding, and since we have introduced that condition that Bj minus Gjx times Uj is equal to 0 for all j. So, if this is not 0, that is a particular constraint j is not binding, so then uj will have to be equal to 0. Okay. So, when uj is equal to 0 for all the constraints, so then the RHS turns out to be 0, and then we simply get dz by dx at x star is equal to 0. Okay. This is what it is saying here. So, when none of the constraints are binding, then the condition of the first order case reduces to the same when we had unconstrained optimization. Okay, that is dz by dx is equal to 0 at the point x star. So, therefore, the first order conditions for a constraint minimum with single variable x are as follows. This is the first set of conditions, and we have to ensure that uj are all non-negative, and in order to ensure that for every non-binding constraint uj is equal to 0, we have this condition, and the optimal solution should be a feasible one. So, therefore, it should satisfy these constraints that are there. Okay. So, these are the first order conditions. Resolve these together for a constrained minimum with single variable. Okay. So, until now we have been assuming that this function z is only varying with x. Okay. So, just take a look at this. So, these are the conditions which ensure that if a constraint is binding, then the derivative of the binding constraint will be having the same sign as the derivative of the function at that point. Okay. So, this is equivalent to that. This is just saying uj is non-negative. This will ensure that if a constraint is non-binding, that is for a particular constraint j, this bj minus gj x star is not equal to 0. So, then uj will be forced to 0, and this is the constraints which we usually have. So, this is just saying that the x star should be a feasible point. So, it should satisfy all the constraints that are there. Okay. So, we will now develop the first order conditions for constraint optimization problems with multi dimensions. So, until now we were assuming that this function z is only varying with one variable x, but now we will be considering the case that there can be multiple dimensions here. So, let us consider an example here where we suppose only have two dimensions, that is this function z is only varying with x1 and x2 here. So that's why you can see that there are these two axes here, x1 and x2, and there are 6 constraints here which are represented by these lines here. These need not be lines, these can be curved also. Okay, so we are not necessarily assuming that the constraints have to be linear, and neither are we assuming that the objective function has to be linear. So you can see that there are these contour lines like this, which are telling how the objective function values are changing. Okay, so there is this direction of decreasing objective function. So if you go in this direction, then the objective function will decrease. Okay, so we have talked about these kind of contours before also. So what it means is that the objective function value has the same value at all of the points here on this line, same the objective function value at all the points on this line, and so on. Okay, so we can write down this optimization problem as minimize this z, which is varying with x1 and x2, such that gj x1 x2 is greater than or equal to bj for all of these 6 constraints that we have. Okay, now since it is given that the objective function is decreasing in this direction, so it is also known to us that the minimum point or the optimal point occurs at this intersection of the two constraints 2 and 3 here. Okay, and therefore these two constraints 2 and 3 are binding at the minimum, that is g2 x1 x star is equal to b2 and x2 g3 x1 star x2 star is equal to b3. Okay, so this is kind of a distinction from the case when there were only single dimension. So there was only a single binding constraint, but now you can have many more binding constraints in multi dimensions. Okay, so the direction perpendicular to any curve of the form this gx1 comma x2 is equal to constant at some point x dash is given by the gradient of the curve at that point, that is by this vector. So we have these two partial derivatives, one with respect to x1 and the other is with respect to x2. Okay, so to understand this, let us look at what do we mean by gradient when we have multiple dimensions. So previously when we had single dimension case, then we had x greater than or equal to a dash as one constraint, and this was the other constraint that x is less than or equal to a double dash, which is equivalent to saying that minus x is greater than or equal to minus a double dash. Okay, so there we were saying that dg by, I mean this is g1x is equal to x, so dg1 by dx is equal to 1. Okay, so in that case, since this is positive, so we say that the direction of the gradient of this function g is in this direction. Okay, because this is the positive direction. Okay, now when we are going to the multi-dimension case, so suppose this is x1 here and this is x2 here, if there is a particular constraint still like this that is saying suppose x1 has to be greater than or equal to a dash. Okay, so for this again the partial derivative of g with respect to, now this is partial derivative, okay, with respect to x1, this will be equal to 1, okay, and the partial derivative of g with respect to x2 will be equal to 0. So then the direction of the gradient will be in this direction. If you have another kind of function g dash, which is suppose saying that x2 is greater than or equal to some a dash. Okay, so suppose you have this kind of constraint here, it is saying that this is a dash now, but we are on the x2 direction, so we have to be always greater than or equal to a dash. So the partial derivative of this g dash with respect to x1, this will be equal to 0, but the partial derivative of g dash with respect to x2, this will be equal to 1. Okay, so the direction of the gradient of this kind of constraint will be in this direction. in the top direction. And now we are looking at these constraints here again. Suppose we have 2 dimensions, but suppose they are in this form, okay, that is we have to be on this side of the constraint. Okay, so if you are looking at the gradient at this point, so it will have 2 components, one will be in this direction, the other one will be in this direction, and therefore the actual gradient direction will be perpendicular to this. Okay. So with this it will be easier to understand that when we have these kind of functions which are varying with x1 x2 also, so then how do we determine the direction of gradients in this case? So the first order conditions for constraint problems when we have multiple dimensions rest on the observation that the gradient of the objective function at this point, that is the optimal point, which is given by grad z x star, must lie between the gradients of the binding constraints. Okay. So here you can take a look at this, that we have these 2 binding constraints, constraint 2 and constraint 3 here. Okay. So this binding constraint, this derivative grad g3 is the one which is perpendicular to this constraint 3 at this point. Similarly, we have grad g2 which is perpendicular to this constraint 2 at this point, and then we were given that the objective function decreases in this direction. Okay, so gradient z is in this direction and minus of gradient z is in this direction. Similarly, for gradient g2 we are drawing minus of gradient g2 which is in this direction, and similarly minus of gradient g3 which is in this direction here. So the important observation here is that the gradient of this objective function must lie between the gradients of the binding constraints, that is this grad z is lying between grad g3 and grad g2. Or if we look at the opposite directions of this, then it will means that minus grad z is lying between minus gradient of g2 and minus of gradient of g3. And why that should be the case? Okay, for example, if that was not holding, suppose minus of gradient of z at the optimal point were to point below minus of gradient of g3. Okay, that is, suppose minus grad z was not here but it was somewhere here. So then this z function could be further decreased by sliding to the right along g3. Okay, but then that will violate this fact that we have assumed that the optimal solution will lie here. So if the minus grad z was actually like in this direction, so then it would be possible to further decrease the objective function value by going in this direction here, and then we will be reaching at some particular point which will be the optimal one. But then this leads to a contradiction because we already assumed that the optimal point is here. Similarly, if minus grad z was above minus grad g2, suppose the minus grad z was in this direction, so then it would have been possible to slide further up here and we would have got to a point where the objective function value is even lower, but then that will lead to the contradiction that the optimal point is here. To better understand this, you can take some further examples and you can see this. Okay, so suppose we have this kind of function here. Okay, suppose we have these 5 constraints here. Suppose the objective function value is decreasing in this direction. So suppose these are some constraints 1, 2, 3, 4 and 5 here. Okay, so the optimal point is here. Okay, now here we have seen that the gradient of z will lie between the gradients of the 2 binding constraints. So here minus grad z is in this direction here, whereas minus of gradient of the second constraint will be somewhere along this direction, so that it is perpendicular to this. Minus grad g2 will be in this direction, and similarly minus of grad g3, it will be perpendicular to this point here, will be in this direction. However, you can check at other corner points. For example, suppose take a look at this point here, which is the intersection of constraint 1 and 2. So, here if you draw the minus of gradient of the constraint 2, so then the gradient of the function g2 will be in this direction. So, minus of gradient of g2 will be in this direction here. Similarly, the minus of gradient of g1 will be in somewhere along this direction, okay, so that it is perpendicular here and this is also perpendicular here. But since we have said that the objective function is decreasing along this direction here, minus grad z will be here. So, you can now see that this is now not lying between these two directions here, minus grad g1 and minus grad g2. At optimal point, this will always be satisfied, because this is the first order kind of condition, the necessary condition. However, if this condition is satisfied at some other point also, it is not always sure that that will also be the optimum, but this is a necessary condition. So, this has to hold. This may or may not be satisfied at other points which are not optimal. Okay. So, I will suggest that you do some kind of exercise like this to appreciate this fact. So, this fact that the gradient of the function z will lie between the gradients of the two binding constraints can be thought of as equivalent, saying that this gradient of z is a linear combination with non-negative coefficients of the gradients of the binding constraints. So, what it is saying is that you should be able to express the gradient of z as some u1 times, or suppose u2 times of gradient of g2 plus u3 times the gradient of g3, where both u2 and u3 are non-negative. So, it is saying that this gradient of the function z at this point can be expressed as a linear combination of the gradients of the two constraints which are binding here. Okay. So, this is this condition that I mentioned. Important thing here is that u2 and u3 both have to be non-negative, okay, because only then it means that we are looking at this kind of scenario where the gradient of z will be lying between them. If one of them is allowed to be negative, so then the gradient of z need not be lying in between these gradient of g3 and grad g2. Okay. To get an intuition, you can see that suppose if u2 is equal to 0, so then what it will be saying is that the gradient of z will have the same direction as the gradient of g3, okay. And similarly, if u3 is 0, so then the gradient of z will be having the same direction as gradient of g2, okay. So, this condition that we have mentioned here, this can be written as in an expanded notation as this. So, since there are two variables here, that is two dimensions we are focusing on. So, what it is saying is that the partial derivative of z with respect to x1 is equal to u2 times the partial derivative of g2 with respect to x1 plus u3 times the partial derivative of g3 with respect to x1. And then again, the second condition is that the partial derivative of z with respect to x2 is equal to u2 times the partial derivative of g2 with respect to x2 plus u3 times the partial derivative of g3 with respect to x3. Okay, so this condition has to hold for every I 1 to 2, that is, it has to hold for every variable x here. Okay, so this is important. So, in order to generalize this condition to problems of this type, that is minimize zx subject to these constraints that we have here, an auxiliary variable uj can be defined for each constraint here. So, let uj be non-negative if the jth constraint is binding at x star, and let uj be equal to 0 if a constraint is non-binding. So, this is the same way we had defined uj when we had single variable. So, then we had said that if a constraint is non-binding, then uj has to be equal to 0. If it is binding, then it may or may not be equal to 0. So, that is why we are saying it is non-negative. Okay. So, the first order conditions can now be written as follows. This is the first condition that we saw, that the gradient of z will be a linear combination of the gradients of the binding constraints. Okay. So, when we were focusing on the single variable case, we had come up with this kind of condition, but from a different perspective. Okay, and this one we have now tried to see graphically, and we are able to appreciate this fact in a different way. And then we have these conditions. So, uj have to be non-negative. Then this condition is ensuring that if a constraint is non-binding, that is bj minus gj x star is not equal to 0, so then uj will be forced to be 0, and the optimal solution x star should satisfy the constraints that we have. Okay. So, these conditions above are called Karush-Kuntukar conditions or KKT conditions, which are named after the mathematicians who have proved that these conditions are necessary for a constraint minimum. Okay. So, there are these three mathematicians here who had discovered these conditions around the same time. So, they have been named after those people. These are very important concept here, these KKT conditions. So, this everyone should be aware of if you are talking about optimization. Okay. So, these auxiliary variables uj are called dual variables or sometimes Lagrange multipliers. Okay. And this condition uj times bj minus gj x star equal to 0 for all j is known as the complementary slackness condition. Okay. Note that if none of the constraints is binding, that is the program is unconstrained, then the first order condition is simply gradient of z at x star is equal to 0, subject to the assumption that this x star is a feasible solution, that is gj x star is greater than or equal to bj. Okay. Why is this? Because again, when none of the constraint is binding, so for each constraint j, uj will be equal to 0. Okay. So, if uj is equal to 0, so the first condition that we saw, that will result into gradient of z at x star being equal to 0, because the RHS in that case is equal to 0, and the other conditions that we have, uj greater than or equal to 0, that anyway is satisfied. The complementary slackness condition is also satisfied, because I mean uj are equal to 0, so this anyway is satisfied. Then only is this, that gradient of z at x star is equal to 0, and the optimal solution that we have found should be feasible. Okay. So, with this we will end in this lecture, and then we will be continuing later. Okay. Thank you.